right. Hello, everyone. Thank you for coming, watching, however you're joining us today. So today we're going to talk basically as the lead maintainer of the Scala.js project. And this talk is not, unlike many of the talks today, it's not so much about Scala 3. It's not so much about Scala 2 either, to be honest. One would argue that this is more a JavaScript talk than a Scala talk, but who knows? Hopefully you'll like it anyway. All right, so we're going to explore what I consider to be the 3 hardest library bugs that Scala.js has had over its entire life. So those 3 bugs are parsing of 32-bit float numbers, formatting of floating point numbers, and lastly, regular expressions. So some of those, I mean, have lingered for months in the issue tracker with no fix in sight. The regular expressions one is actually much older. It dates from basically the very early days of Scala.js. And so basically that bug report has been open for like 7 years at this point. So for a very long time, we thought those things were basically unfixable. And in the past few months, I've taken a really hard look at those issues, and we did finally come up with fixes for those. And so we're going to explore why those are hard problems and how we fixed them. So let's go into 32-bit floating point number parsing. To set the stage, we're only looking at decimal notation here. Hexadecimal notation has its own set of problems, but not nearly as fundamental as for decimal notation. We're only looking at valid inputs that are finite, so no nans, no infinities, and we're only looking at non-negative inputs. So basically, we assume there is no minus leading sign. If there would be one, we would just take the opposites of the result. So a typical example input that we're working with is 123.456, an exponent, and minus 16. So the exponents can be negative, but not the entire number as a whole. Before looking at parsing floating floats, 32-bit floats, let's just have a look at parsing doubles. Parsing doubles is extremely easy to get right because JavaScript has a built-in function which it calls parse float, but it actually parses a 64-bit floating point number, so a double in Scala terminology. So the way we implement parse double in the Scala.js library is calling JS dynamic global parse floats and then casting back the result as a double. Now, the way we had implemented parse floats for about like 7 years also is by calling parse double and then converting the result to a float. Since double has a higher precision than float, you would expect that to always return the correct result. And by correct here, I mean the float number that is closest to the decimal number that the string represents. And it turns out that this is not correct. And someone at some point reported an issue that if you give it that specific input string that you have here, it will return as a result something that ends with 51, but the expected output, so the one that the JVM would answer for the same call, ends in 37. So if you're not super familiar with floating point numbers, this is not like a huge jump. Those float numbers are actually very close to each other. Even better than that, they're like adjacent. Like there is no float number that sits between those 2 numbers, right? So we're only 1 float away from the correct result. So how come? Like we're parsing a double, and then when we convert that to a float, it's got to be the correct result, right? To understand why this doesn't work, let's set aside floating point numbers for a moment and look instead at normal mathematical decimal numbers, right? And consider this problem. I give you any number in decimal notation, and I ask you to round it to the nearest 1,000. But there is a catch. You're only allowed to use two primitive functions to do that. One is rounding first to the nearest whole number, so integer number. And then given the whole number, you can round it to the nearest 1,000. So if we use those two primitive functions to round any number to the closest 1,000, we could try with an input like 3,534.7 that would round to the nearest whole number as 3,535. And then when we round that to the nearest 1,000, we get 4,000, which is indeed the closest 1,000 to the original input. If, however, we take as original input 5,499.7, that first rounds upwards to 5,500, because indeed this is the closest whole number to the original input. But then when we round that, we have to break ties, because that is exactly in the middle of 5,000 and 6,000. And here the tie-break rule says round upwards, which in this specific case is not what we want, because we round upwards to 6,000, but that is not the closest 1,000 to the original number. The closest one would be 5,000. So you can see that this happens if the original input is really, really close to what we call a midpoint. So a mathematical value that is exactly in the middle of two possible results. And this is exactly what happens when we use parse double to parse a float, because we're essentially taking an arbitrary decimal number first, rounding that to what a double can hold, and then we round again the double to fit in a float. And if the original input is very, very close to a midpoint between two floats, then we can get into this problem. All right, so now to go into the solution to this problem, I have to give you a little refresher on floating point numbers, how they are encoded in the machine. So you can see here a picture of a floating point number. You can see that it has one sign bit, a number of bits for the exponent, and then a number of bits for the mantissa. And the actual mathematical value that this represents is -1 power to the sign, so that's 1 or -1, times 1 point mantissa, and that's mantissa written as a binary number interpreted in binary. And then all of that times 2 power exponent minus 127. This is a constant that is specific to 32-bit float numbers. Remember that we said we would only look at non-negative inputs, so actually we can get rid of the sign in this problem, and we're only looking at 1 point mantissa times 2 power exponent minus 127. If from that formula we declare a couple variable, m, which is 1 mantissa, and I really mean here like string concatenation of the binary bits, and then we declare n as being the number 23, and k, which is the number of bits in the mantissa, and then k as exponent minus 127 minus n. Given those variables, the value that is represented by a floating point number is actually just m times 2 power k, with a constraint that m sits within 2 power n and 2 power n plus 1. Okay, then I also have to give you a refresher on decimal notation, which you may have learned in school, most likely. If I write 123.456 e minus 16, this actually stands for 123.456 times 10 power minus 16. Again, we can play the same kind of generalization, and we can say that this is an integer point, a fractional part, times 10 power an exponent. And if we declare f to be the string concatenation of int and frac, and e being the exponent minus the length of frac, so literally the number of digits in the fractional part, then the value that is represented here is f times 10 to the e. So the parsing problem boils down to, given as input f times 10 to the e, find m times 2 to the k with the constraint that m is within certain bounds. And this is actually a very, very hard problem that was puzzling researchers for a while. And the basically definitive answer to that problem was provided by William Klinger in 1990 in a seminal paper called How to Read Floating Point Numbers Accurately. And this describes an algorithm which is called Bellerophon. And today, basically all languages and standard libraries use a form of Bellerophon to parse their floating point numbers. So, all right, we could just re-implement Bellerophon in Scala.js to parse 32-bit floating point numbers accurately. Except this is hard. There's a lot of corner cases in that stuff. We would have to really test a lot of things, but the most problematic thing is that it works on big integers. And we don't really want to use big integers, at least not all the time, because that is slow, especially given the fact that in most cases we have to implement big integer again in user space in Scala.js, right? So can we avoid it somehow? Well, there is one aspect of the Bellerophon algorithm that was really interesting for us. And that is one specific subroutine, which is called algorithm R, which takes the inputs f and e, and then an approximation z, so it's a floating point number, that we expect or we hope is fairly close to the correct result. And given those things, this algorithm will find the correct answer by iteratively going up or down to get to the closest value to f times 10 to the e. The way it does that is extract the bits m and k from the floating point value, and it compares f times 10e to m times 2k. But this is hard because those numbers are not necessarily whole numbers, because e and k, even though f and m are integers, e and k can be negative, creating fractions in the second factor. So the way they do that is they compute integers x and y that are integers, and preserve the property that x over y is f times 10e over m times 2k. The way you do that is simply that you move 10 to the e to the other side of the equation if e is negative, and in the other direction for 2 to the k. And then you compare x and y, and that gives you the same result as comparing the original numbers. And then if x is equal to y, then you apply the tie-breaking rule. If x is greater, then you try again with the floating point number that is just above. And if it's smaller, you try again with the floating point number that's just below. And then algorithm R has a bunch of very complicated terminated conditions to know when to stop, right? So here are the insights that we found. First, from the paper, there is a proof in there that says that we cannot avoid big integers at some point. So at some point we say, okay, I need big integers. I can't completely avoid them. And the second thing is, if we have a z, an approximation that is at most one float away from the correct result, we can apply something like algorithm R to find the correct result in one step. And from our own analysis of the problem in the JavaScript context, we can get an approximation z with parse double dot to float. And that is actually at most one float away. And moreover, it is correct, except if parse double returns a midpoint between two floats. Given that, we created our own novel algorithm given the constraints of the JavaScript environment. And this is how it works. So take a good seat here. So first we use parse double and we store the result in Z0. And then we compute Z0 to float to have an initial approximation Z. If Z0 is not a midpoint, we could jump to step 5 where we just return Z. But to decide that, we will compute a pair Z down, Z up, which are two adjacent floats that enclose Z0, which is a double. And that we can do by computing either the pair Z next up Z if Z is smaller than 0, and otherwise next down Z and Z. Once we've got that, we can check whether Z0 sits exactly in the middle of those two floats. And if yes, then we have to apply something like algorithm R. So we reparse f and e this time as a big integer and an integer from the string s. We extract m and k from the double Z0, and then we compare f times 10e to m times 2k using the same trick with x and y that algorithm R uses. And finally, if x equals y, we tie break, and otherwise we return z up or z down. And that's it, right? In one step with no iterative algorithm, just a constant number of operations. So that fix was shipped in Scala.js 1.5.1. It was also shipped along with a fix for a similar issue in hexadecimal parsing, but the fix there is much simpler. It's not as fundamentally difficult. And that actually turned into someone reporting then that the long to float conversion was actually also erroneous in a similar way, and so we fixed that. It's going to ship in Scala.js 1.6.0. So that's it for 32-bit float parsing, and let's move on to the second problem, floating point number formatting. And in this case, I mostly mean doubles because floats behave the same. So here we're really looking at the %f format specifier of java.util formatter that you may also use through string formats or through the f interpolator in Scala. There are exactly the same issues and the same fixes for %e and %g, but we're not going to discuss them today, right? It's exactly the same story. And again, we're only going to look at finite inputs, so no nans and no infinities. When you use the %f formatting specifier, you can specify a precision p using %.p and then f. It has a default, which is 6. And in the case of f, it represents the number of digits after the dot. So here is an example. If your input is 123.4556 as a double value this time, and you use the format %f, you would get 3 added zeros because you need to go to 6 digits after the dot. If you use 0.8, you'd get more zeros. If you use 0.1, you remove significant digits, and that means you have to round. In this case, round up to 123.5. And you can actually go all the way to 0.0, in which case you round to the nearest whole number. All right, so that sets the problem. Now, the way we had implemented that, and which turned out to be wrong, was, well, actually, ECMAScript or JavaScript has a method toFixed that takes a precision and formats a double value using fixed notation with a given precision, so a given number of digits after the dot. That seems like perfect. It seems like it's the right way to implement this function, except that if you use a precision of 11, and that particular input, I mean, there are zillions of other such cases, but this is one case where it shows up, then the JVM will format it with something that ends in a 0, and the JS with something that ends in a 1. How come? Well, it turns out that the spec is different. JS chooses the value that is closest to the true value that this double represents, which is this huge number that continues with many more decimals. But you can see at some point it has this 0.6. And using a precision of 11, we're really cutting between this 0 and this 6, throwing out the 6 and the rest. And so if you round that, you're supposed to round that up to a 1. So why does the JVM not do that? Well, the JVM has a different spec. The way it's specified is first, find a string representation that uses as few digits as possible to uniquely identify the double value that we have. And then once you've done that, if you don't have enough digits after the dot, just appends zeros. So the spec is different. So what do? Well, we basically have to re-implement that. We didn't find a way to leverage toFixed in a way that would do the right thing. And here we enter another problem, which is how do you format a floating point number, and how, especially with as few significant digits as necessary to uniquely identify the double. And that turns out to be an even harder problem than the previous one. This one has been going on for decades, with many improvements over the decades. And the latest incarnation of that is by Ulf Adams in 2018. So it's fairly recent, with the Ryu algorithm in the paper, Fast Float to String Conversion. So again, we could take that paper, take its algorithm, re-implement it in Scala.js, and it would be a done deal, right? Well, except that the problem is that it uses huge pre-computed tables. And while that is fine in a C binary or in the JVM that you ship, it's not fine to embed those huge pre-computed tables in every Scala.js application in the JavaScript that you ship to people, right? So it's impractical in a JavaScript context. Okay, so is there anything in JavaScript that already gives me the required number of significant digits and that I could leverage in some way? Well, it turns out there is, and it's called toString. So if you take a floating point number and you call toString on it, it will return you as few digits as necessary to uniquely identify that double. Except that it won't always format it using fixed notation. Sometimes it will format it as with scientific notation, like this example. So what do we do then? Well, we receive that string, and we somehow have to emit a fixed notation instead, right? Well, we're going to parse it. So in order to format a double value, we first call toString to format it as a string, then we reparse that string, and then we re-emit it in a different way. I'm not kidding. So the way that we parse it is we identify those four components: the exponents, the fractional part, the integer part, and the sign, and then we build our own representation of a decimal number, which has a negative flag. It has an unscaled value, which is a concatenation of the integer part and the fractional part. And it has a scale, which is computed as the fractional part of length minus the exponent. And then what an instance of decimal represents as a mathematical value is -1 power negative times unscaled value times 10 to the minus scale. Right. Once we've done that, we've used toString, we've parsed it back into a decimal, and then we have to format the decimal into fixed notation. And to do that, that actually becomes now a very easy problem. We just have to reset the scale of the decimal so that it's exactly p, the expected precision. If p is greater than the scale, we append zeros. And if p is less than the scale, we have to drop scale minus p digits at the end and round with tie-breaking upwards in this case. Once we've done that, we just insert the dot at position length minus p, and finally we add the leading minus sign if negative is true. So as an example, if we have 123.456 and we are asked to format it with a precision of p equals 6, we will parse it as a decimal instance with false. The string 123.456, right? It's really a string of decimal digits. and the scale is 3 because there are 3 digits after the dot in the input, and there is no explicit exponent, so the exponent is 0. Once we've done that, we set the precision to 6, and that means we have 3 more precision, so we add 3 zeros. And finally, we take that string, we insert the dot at the right place, and we get the correct result. The last thing I want to say about this topic is rounding, and especially with carry. And this is exactly like you learned in school. So remember, we have a string of decimal digits. So if we have to cut out the 78 and round, in this case upwards, because it's greater than 5, we look at the last digits, we see it's a 2, okay, that becomes a 3, and I create a new string with that. And if it's a 9, I set it to 0, I move on to the next digit, I increase that one, and that gives me 360. And that goes on, and it can go actually on all the way to the top. If I have to round upwards something which is a string of all 9s, I end up with 1 and zeros after that, which gives me 1 more digit than what we started with, which actually complicates the algorithm to some degree. All right, finally, once we've done all that, we can format doubles using fixed precision. And as a bonus, we can actually format big decimals as well for a very small cost, because a big decimal has an unscaled value, which is a big integer, and it has a scale as well. And so we can extract those things, extract the negative, the minus sign, we create a decimal from that, and then we ship that decimal to the formatting routine, and we can format big decimals for basically free at this point. So that's it for floating point number formatting. That shipped in Scala.js 1.5.1 as well, along with also the same technique for formatting in scientific notation and general scientific notation. And in the same release, but it's kind of unrelated, but we also shipped a correct hexadecimal notation formatting for floating point numbers. Finally, let's get into the topic of regular expressions. So JavaScript has regular expressions in its standard library under the regex class. So you can create a regex with the regex itself and then flags. Like here we use FO plus as the regex and the U flag, which stands for Unicode. And the thing about JavaScript's built-in regex is that modern JavaScript engines, they literally JIT compile the regex to native code. So there is no way we can beat that in userland. If we were to re-implement a regex engine ourselves, it would perform at least an order of magnitude slower than the native regex. So for performance reasons, we don't really have a choice but to reuse the native regex in order to implement java.util.regex pattern. The way we used to do that is that in pattern.compile, we would just like translate the API of pattern into the API of regex. So if we had the case insensitive flag, we would use the JS flag I. For multi-line flag, we use the JS flag M. And then the regex is basically given as is, except that we recognize 2 specific shapes that are used in the Scala standard library, which is kind of ridiculous if you think about it. So first we recognize like quotes, single car, end quotes, which we then like programmatically quote the C instead. And we can also recognize leading embedded flags, which we extract and convert to JS flags. The problem is that this is basically wrong. It's been wrong for 7 years. And many people have reported a bunch of issues. This is a collection of issues that people actually reported. So they ran into those problems. The S or .all flag has no effect. There is no general support for QE. The string.split array of cards doesn't work because it uses QE inside. The JVM, and this is a fun one. Like if you use \s, JVM and JS actually disagree on the set of characters that this represents. If you use Unicode categories, it doesn't work. The worst one, I think, was this weird intersection thing, which is Java regex thing. And it actually parses in JavaScript, but it does something completely wrong. It has nothing to do with intersections. So this is actually terrible because you get like soft failures. And then no support for atomic groups and POSIX character classes. And that's only the ones that have been reported by users. There are zillions more. In fact, as I was trying to fix these issues, I discovered that the set of things that actually work is very limited. Like it's, well, ASCII characters and no predefined character classes and no flags, basically. Like it's very, very limited. So what do we do to fix that? Well, I'm a compiler engineer, so I'm going to compile all the things. And so I'm going to actually implement a complete parser for the Java regex, and then compile every sub-pattern to an equivalent JS regex pattern that will do the same thing, even if it doesn't look like the same thing, right? So first, what flags do we use? Well, we always use the U and S flag if they're supported, because they will bring us Unicode support, as in like correct handling of surrogate pairs. So a pair of two cards that represents just one Unicode code point. And the S flag for .me, meaning any character. And if those are not supported, we detect that at runtime, and then we complicate the way that we compile the regexes so that we emulate the behavior of U and S. And then the only other flag that we use is the I flag for case insensitivity, but only when both case insensitive and Unicode case are on. If case insensitive is on, but Unicode case is false, then we instead compile every ASCII letter as a character class with the lowercase and the uppercase variant, and in character classes the same, and for ranges as well. Then for the actual patterns, I'm not going to go into like all of them. I'm just going to illustrate a couple very interesting ones. So first, this is the set of things that we can compile as is without any specific treatment. So we have sequences, alternatives, greedy quantifiers, lazy quantifiers, non-capturing groups, look-aheads, and finally look-behinds, but with a catch. They will only be available if you configure your build to say, I rely on ECMAScript 2018, because ECMAScript 2018 added support for look-behinds. So we can simply compile them as is. If we don't have support for look-behinds, there is no way we can polyfill them or compile them somehow. If you know a way, please come talk to me after the talk in the virtual chat or something, because I'd be very interested in a solution for that. Now, for single code points, like just regular characters that you encounter in the pattern, what we do is we first parse it, and then we re-emit it as just the value that it represents as a character. So if we have an A as an input, it becomes an A, or maybe it can be a character class with an uppercase A and a lowercase a in case we have to apply ASCII case insensitivity, right? And that's the reason that we really parse the thing and then compile it back, because if we have a \x for 1, that also stands for an uppercase A. And even though JavaScript would understand that escape as is, we still have to parse it, understand that it's an uppercase A, to decide whether we have to emit it as a character class for the uppercase and lowercase one. So since we have to do that anyway, we take the opportunity to just re-emit it as the value that it has. And if we have a meta character, then we escape it with a \. And one fun fact is that if you have \u escapes for a pair of surrogate characters that form a single code point, that double escape actually stands on its own. It's an indivisible unit. That means that Unicode code point. So we also parse it as a whole and emit a single code point, in this case, the musical G clef. All right, now for the things that become a bit hard. Predefined character classes, they depend on the value of this Unicode character class flag, whether it's present or not in the JVM pattern. So for example, for \d, which is a digit, if the flag is off, that's only ASCII digits 0 to 9. But if it's on, it's any Unicode code point that has a Unicode general category being ND for a decimal number. So we check the flag and we emit it in two different ways. Same, for example, for the negative word character, which if we're only in ASCII mode, it's that specific set of ASCII characters that we have to avoid. But if we're in Unicode mode, it's we have to avoid a number of Unicode general categories and binary properties. And so we expand that into this monstrous regex that uses Unicode properties. Another one that I want to talk about is the start of input, the caret, because it feeds into the multi-line flag, and it shows why the multi-line flag cannot actually be translated to the M flag in JavaScript. So the meaning of caret depends on two flags. First, multi-line, and then if multi-line is true, it also depends on Unix line. So first, if multi-line is false, that's easy. We compile the caret as a caret. It matches the start of the input. That's it. But if multi-line is true, and then Unix line is true, the caret is supposed to match either at the start of the input or right after a new line character. Another way to say it is that at the point where we are, we can look behind to see if there is either the start of input or a new line character. And this is exactly what we do here. We use a look behind, and instead we look for the start of the input or a new line. And that requires to use a look behind, which is only available in ECMAScript 2018. So multi-line will only work in ECMAScript 2018. It gets worse if a Unix line is false, because then we have a bunch other set of things that can be new lines. First, we have this 85, we have 2028, 2029, and then we have the carriage return, which is the macOS new line. But there is a catch. If you're in the middle of a carriage return and a new line, you're in the middle of a Windows new line sequence. So you're not at the start of a line, you're in between lines. In a no man's land. And so you're not supposed to recognize that as a start of a line. And JavaScript get this wrong in a sense. I mean, it doesn't have the same spec. But for the JVM, we have to avoid that. So when we look behind, we see a carriage return, we also have to check when we look ahead, we don't have a new line character, which is quite involved and mind-bending if you think about it. One of the last things I want to highlight here is how we compile custom character classes, and more importantly, because we have intersections. Like, remember I said earlier that the intersections would parse in JavaScript but do something completely different? Well, so we have to compile them away also. So if we start with easy cases, let's say we have a range C to F, that would typically give a range C to F. But if we have to apply ASCII case insensitivity, then we have to duplicate the range for the uppercase and the lowercase variant. And then we have a bunch of more complicated cases, like if we have a \d, so a predefined character class embedded within the custom character class. Normally, we simply expand it in place, right? It gives caret A, 0 to 9, and then C. But some of those predefined character classes are themselves defined in a negated way. So the next example with 2 and \d5 means I want anything but 2 or 5 or anything that is not a digit. And that becomes quite difficult, but you can see it as an intersection. You can say, I don't want something that is not a digit. And also, I don't want a 2 or a 5. And the way we compile this intersection is using a look-ahead, in this case, a negative look-ahead. So the question mark bang is a negative look-ahead of not a 0 to 9. So actually, this could be simplified to a positive look-ahead of 0 to 9, but that's not how the engine works. And once we've done that look-ahead, then we also check and match something that is not a 2 or a 5. And we can apply that to also like normal intersections, like A to Z and not M to P. That would become a look-ahead of A to Z, followed by a negative character class of M to P. And finally, we can do that even for negated character classes that have intersection within, and then we distribute the negation over the intersection, which then becomes a union because of the Morgan's laws, right? And so we have not an A to H or not a D to P. And we can apply those rules in a general way to compile away any kind of complex character classes that are thrown at us. The last pattern I want to share here is a fairly obscure thing. It's called atomic groups. If we have never hit the kinds of troubles you can get that require atomic groups, you may not even be aware that this is a thing. I certainly was not aware of it before I started fixing all these regex issues. So there's no shame in that. And just to set a bit the stage, it can be a solution to some problems of catastrophic backtracking. Like if you have this x plus, and then all of that plus, and then followed by a y, and you try to match the input, which is a string of all x's, it will take an exponential time because of backtracking to decide that it doesn't actually match the regex. And you can avoid the exponential time by wrapping the thing in an atomic group. The atomic group says, first match what's inside the group, and either you don't succeed and well you backtrack to before, or you do succeed, but then you put that with you glue all of that together, and you're not allowed to decompose it again. So if you have to backtrack later, you backtrack all the way to before the atomic group. You don't backtrack inside the atomic group. So here it's not only about correctness of the result, it's also about having the right performance profile. And this I thought I would never be able to compile away, but thanks to a blog post by Stephen Levitin, who found a way, a crazy way to mimic atomic groups if you have look-aheads. Because you can use, so to compile the atomic group with an X, you define a look-ahead, and inside the look-ahead, a capturing group with inside the X. And then after the look-ahead, you use a back reference to the capturing group that you just used. And because the look-ahead is non-backtracking, this does the right thing. You first look ahead the thing you want, then you go back, and then you match exactly the same thing, but that's a single unit that you will backtrack in one go. And with that, we can also implement possessive quantifiers because there's syntactic sugar. And that's it. We have a couple of things that are still not supported. If you have ideas on how to support these, please come and talk to me. To conclude, the cost of the operation was 12 kilobytes of JavaScript code in the full opt.js version to implement the parser and the compiler. Basically, this is a hit that we decided to take for the sake of correctness. That work is in a pull request that's under review. It will likely ship also in the upcoming version of Scala.js, so Scala.js 1.6.0. That concludes this talk, and I will be more than happy to take questions. I have loads of backup slides to answer all the most advanced questions you may have, so please fire away.
Hi, Sebastian. Thanks so much for your talk.
My pleasure.
We do have a few questions, and the first of which is, you stated that implementing the full Bellerophon would be slow. Is Java's parse float doing something else that is faster?
No, it is doing a Bellerophon, except that that Bellerophon is written in C in the JavaScript engine, and it has so it uses probably GMP for the big numbers or something. I mean, basically, it's just a matter of if you have to re-implement all the big integer logic in Scala.js, it's compiled to JavaScript, and then performs all of that, it's completely insane compared to leveraging the Bellerophon that's inside JavaScript implemented in C, using all the crazy tricks that they have. So this is basically the idea here. But no, it's doing the same thing, just in C and not in JavaScript.
All right, the next question we have to answer live is, did you look at how other languages implement or specify the specifications?
Yes, I did. And the thing is, nobody does that. We are in a very unique position where we are, so first, for parsing the 32-bit float numbers, well, you have to realize that most languages that compile to JavaScript don't even have the concept of a 32-bit float. They only have 64-bit float. And for the ones that do, like Kotlin, they simply say floats are 64 bits anyway. I don't care. Like, even if on the JVM it's 32 bits, on JS it's going to be 64. So they will be doubles basically. And Scala.js seems to be like the only language that really sticks to the 32-bit semantics for the floats. As for the other two problems, well, first it's limited to Java-like languages because they're related to specific specifications from the JDK, right, that we have to implement on JavaScript. And again, we can look at Kotlin or Ceylon or other languages that compile to the JVM and to JS. And it turns out that they all say, whatever, I'm just going to compile regexes as JS regexes like we used to do. But our criteria and our requirements for quality of the JDK implementation are much higher in Scala.js. Like we have virtually no bug in there. If it links, it works. And so those three problems were the three pain points that we had, where we had to say, okay, it links, but it doesn't really work. And so fixing those three is a huge direction. It's a stepping point between most of it works to all of it works. And no other language does that. The other languages that target the JVM and JS, they just say, okay, whatever. I'm just going to use what JS gives me. And I don't care if it's not the same as the specification.
Well, thank you. We have one more question, time for one more question for you to answer live. It is, how did you test the regex transformation function? Did you use any property-based testing?
No, I did not. We don't have a framework for property-based testing. However, we have our infrastructure is such that when we write our tests for the JDK implementation, the tests themselves cross-compile for the JVM. So we write lots of tests that we test against the JVM implementation to make sure that the tests are correct. And then we run the test on the JS version against our implementation to make sure then that our implementation matches the tests. So then it comes down to be really exhaustive about writing your tests. And we have thousands of lines of testing code for the regexes to test all of the possible combinations we could think of. That's it. Like, it's just exhaustive tests, like for everything else about Scala.js. Like, it's
great. Well, we do have a few more questions in the stage Q&A area. If you wouldn't mind taking a peek at those and maybe answering them with the reply function in text,
sure,
we would be absolutely grateful for it. For everyone, that concludes our live Q&A session. Please stay tuned for our next talk with Adam Worski. And again, Sebastian will be answering the remaining questions in the stage Q&A tab. Thanks so much, Sebastian. Happy to have you here.
Wow.